Welcome to today's Manufacturing Engineering Media webinar. Our presentation is Precision Turning Advancements Beyond Belief. Hello, I'm Jim Sawyer, Senior Editor at ME Media. Before the presentation begins, I'd like to provide some background on what we will be doing today. Our sponsor, Hardinge Incorporated, provides a wide range of turning, milling, grinding, and work holding solutions supporting aerospace, automotive, medical, energy, construction, agriculture, mold, tool and die, and other applications. In this presentation, you will learn how precision hard turning of parts is a more efficient alternative to slower semi-finish and finish grinding operations and is a great aid to productivity. You will be able to ask questions during the presentation using the Q&A box that will appear at the right of your screen. Time permitting, these will be answered following the presentation. If time runs out before we can get to all the questions, we will make sure the answers are emailed to you. If you experience difficulty during the presentation, please let us know via the Q&A app. Also, if you have questions about any other aspects of our webinars, please email me at jsawyer@sme.org. Our presenter is Hardinge Applications Manager Tom Sheehy. Tom has been with Hardinge for 30 years and has better than 20 years of hard turning experience. He began at Hardinge as a machinist and has a degree in mechanical technology. In addition, Tom has been trained and certified by Kennametal, Sandvik, Valinite, and Sumitomo in selection, application, and implementation of cutting tools. Now, here's Tom Sheehy.
Thank you, Jim. And first off, I'd like to thank everyone for taking the time out of their busy schedules this afternoon to attend this session. And hopefully you'll pick up some tips and maybe some tricks and some ideas to help you in your quest to get to precision hard turning. Let me start off with the first slide here, that some of the key takeaways from this webinar that hopefully you'll pick up. From expectations and benefits of precision hard turning, we're going to look at some time savings and process and setup reductions when compared to grinding, achievable accuracies and form tolerances and surface finishes and some CPK data and some cutting tool life information, as well as what are some of the challenges of precision hard turning today. You know, the experience levels that are out there now, requirements of the machine tool, the selection of some proper cutting tools, some processing information, and some tips and tricks, things of that nature, along with what's actually the proper measuring equipment that you may need nowadays to get into some of this higher-end precision hard turning. We all know you can hard turn on any CNC lathe, but can your lathe do precision hard turning? With today's technologies and design tools, Hardinge has been able to actually get down into the grinding tolerance areas. If you look at the chart on the screen here, we've basically broken it down from 0 tolerance up to around 11 to 12 micron. And you'll notice that from about 5 micron up to the 11 to 12 micron total tolerance range, that's really what we consider general precision turning. If you notice, the super precision and precision hard turning kind of goes from about a half a micron to 6 micron, so it overlaps into general precision turning and down into the grinding and diamond turning areas today. And that's been done through new design features and technologies and control technologies that we have in the machine tools today that I'll do a little bit more explaining as we go through the presentation. If we look at the direction of accuracy and machine requirements over time, what we've found is that the development, what's actually happened is if you look at the farther left side of this chart, back 20 years ago, 30 years ago, you'll notice that as a percentage of the total part tolerance, and obviously the total part tolerance back then was greater, you'll notice that the form tolerance was not quite as critical back then. Form tolerance on this chart is designated as the light gray area. The lighter blue area is the actual total tolerance added on top of the form tolerance. So you'll see back, again, 30 years ago, we were talking about plus or minus maybe 30 microns as a total form tolerance. Well, over the course of time, you'll notice tolerances have tightened up, and that's probably become true in your industries and in your manufacturing facilities. And as that total tolerance has become tighter, now we see that form tolerance has become much more important when it comes to precision hard turning. And we'll talk a little bit more about form tolerance as we go along, but basically what we're talking about is cylindricity, part roundness, and straightness, because when we're trying to hold a plus or minus 2 micron total tolerance, cylindricity now becomes a very large factor. So that's what we talk about form tolerance. The way that we view the hard turning market today, you'll notice this is an upside down triangle. The top section is where we think about 95% of the market is today. They're doing hard turning. They're removing metal for finishing operations. They may be burning through inserts ineffectively or inefficiently because they don't really understand the technology behind the CBN contents and edge preparations and some of the other things that are involved. They're holding rough turning tolerances of, maybe plus or minus a 10 micron, 12 micron range. Typically, they're struggling to hold a tighter tolerances, but they are seeing the benefits of hard turning, but with a higher cost. Where we really see the precision hard turning or the future of hard turning going is more so towards profile tolerances, where we're talking accuracies of under a micron. Very, very fine surface finishes down in the 6 range. Maximizing tool life and the ability to hold very, very tight CPK or SPC requirements. And some of the key industries that we've been dealing with here in the past couple of years are the gauging and bearing industries, tooling manufacturers, obviously mold and die is very big into it, the power industry, and a lot of the grinding houses now that are trying to minimize grinding or eliminate grinding altogether through the use of precision hard turning. Beginning back in the early 80s, Hardinge came out with the super precision machines, and in 2010 we challenged our engineers to create the highest performance production turning center that's available off the shelf. Now keep in mind there are higher end machines out there than what we produce, however typically they are at a much higher cost. And along with that associated cost becomes support and everything else. But these machine shops typically holding tolerances, typically reserved for grinding, while giving you the flexibility of a standard turning center. When we look at some of the requirements for precision hard turning, really what's required in the machine? Well, you'll notice over on the right here we've got a little key blank up there, and really system rigidity is the key, where we really have to look at the rigidity of the complete process, the system, the tooling, the machine base, etc. We also look at the requirements of a high accuracy spindle, somewhere in the quarter micron runout area. Again, because when we start looking at form tolerance, on a tight tolerance, we have to have a very accurate spindle. We need a machine base with very high static and dynamic stiffness to absorb all the pressures from hard turning. We need a high accuracy, low friction guideway system, which gives you the ability to interpolate a very highly accurate small moves. For those of you in the grinding industries, that's also known as what's called a step test. A lot of times grinders, when they go to qualify a machine, they have to do a step test. We do a very similar thing here at Hardinge when we look at the ability to interpolate highly accurate small moves. And in order to do that, you have to have high accuracy axis positioning feedback. So we have a 1/10 of a micron control resolution, but we have a glass scale resolution of 0.01 micron. So it's 10 times finer than what the actual control resolution is. And that's a direct measurement system which utilizes linear glass scales on both the X and Z axes. We also have an integrated heat vibration management system, and what that does is it, as opposed to thermal compensation, we actually have elected to go to a thermal management system where we don't introduce any heat into the machine environment through the use of chillers and some other things. When we start looking at form profile tolerance, particularly when it comes to spheres and sphericity and arcs and angles and things of that nature, you really have to start taking a very close look at certified tool nose profiles and radiuses, because that becomes a very, very key element when we're single pointing a part. We look at the applications experience of not only the operators and the manufacturing engineers, but also the tooling engineers that are going to come in and help you. And then really key, and we'll spend a pretty good portion on proper cutting tool selection. If we take a look at some of the machine technology advancement over time, this is just some information, again, based here at Hardinge, but if you look at the chart on the screen here, before 2000, just as an example, the Z-axis alignment, back then we were running just under 10 micron. In the early 2000s, mid-2000s, we were able to get that down to around 4.5 micron, and today we're down at 2.5 micron, and that's for the total Z-axis running length of the machine. So the total Z-axis travel alignment is now less than 2.5 micron. That's done through new manufacturing processes and assembly processes, design processes, as well as control technology that's out there today, and some control technology that Hardinge has developed that gives us the ability to put in things such as straightness error compensation, where we can electronically tweak the machine for inaccuracies that may have occurred during some of the build functions or during the assembly process. When we look at hard turning or precision hard turning, we basically here we break it down into two areas. On the left you'll see general hard turning, pretty much plus or minus 10 micron on diameter, some fairly wide open finishes, and around a 5 micron part roundness. That's pretty typical. Most people are doing that today. When we get into precision hard turning, we're looking now more at a total tolerance of plus or minus 2.5 micron or tighter on diameter, a lot finer surface finishes. But you'll also notice, under 1 micron part roundness. Again, because when we start looking at holding a 2 micron total tolerance or a 3 micron total tolerance, part roundness, cylindricity, and form actually become much more critical. Down along the bottom, you'll see a human hair. That's approximately 0.03 of an inch or 63 micron. And general hard turning accuracies and our machine accuracy, and then our resolution. Just to give you a sense of the scale of the sizes that we're talking about here. A lot of customers wonder why you want to go to hard turning, and this has become, these are some of the real reasons that customers look at hard turning. There's obviously increased metal removal rates, which is probably the biggest key that most customers look at going to precision hard turning. When we're talking 3 to 5 times faster than grinding, typically, if not faster. A lot less reduced machine downtime. There's no need to dress the wheels. You don't have to indicate the part in on a mag chuck and a lot of other types of things of that nature. So you have reduced machine downtime, which makes you more productive. You have reduced tool cost. You'll notice on the right there's a special form grinding wheel versus an off-the-shelf PCBN or CBN type insert. So off-the-shelf inserts versus special grinding wheels for the generation of complex shapes. It also gives us the ability to change that shape if we need to, based on what the engineer's thoughts are. Or if there is a part print change, it's much easier to change it with an off-the-shelf insert versus a special form wheel. Obviously, the elimination of certain finish grinding operations, that's another big key area. But one thing that a lot of our customers also do is they will go and eliminate maybe a semi-finish grind operation where with a precision hard turning we can now leave much less stock for a finish grinding operation if grinding is required due to surface integrity requirements. So you have also increased production as possible with more flexibility, meaning that you're more than likely going to be able to achieve a lot of these features and benefits with the use of existing equipment that you may have in-house. It's also increased capability to automate. It's a heck of a lot easier to automate a lathe than typically it is a grinder, as well as machine costs, and there's a whole bunch of other factors that factor into this, but this is some of the key ones that most customers look at. If we take a look at a precision hard turning process improvement example, this is an example of a component that we manufacture here at our facility where we have a 10 micron total part tolerance is required on mainly the right end of that part, which is the ID, the OD, the taper, the face. And you'll notice over on the right side of the chart, we have the grinding process, which was the traditional process, which shows the setup and grind times for 3 separate operations versus the hard turning process. And really what you want to look at here is the setup time reduction going from 85 minutes in grinding to 25 minutes in hard turning, and the run time reduction from 183 seconds down to 83 seconds. So those are substantial numbers, and that's really what drives a lot of customers to investigate hard turning and getting to the precision level of hard turning. When we start looking at measuring equipment, you really have to have the right measuring equipment to be able to check down into the micron or sub-micron range. So you need the ability to measure roundness and cylindricity, profile accuracy, surface finish, and straightness, and these types of things. Here we actually use a couple of Zeiss products, and I'm not going to elaborate on them, but you really have to think about what type of measuring equipment you have in your facilities that you can utilize to be able to measure down into the sub-micron range. Where did it go? I lost the slide. How do I get it back? Push to audience. I don't know. Bear with us here just a second. Here we go. We got it back. Sorry about that. I must have hit the wrong button. When we start looking at some process strategies for precision hard turning, the key thing here to remember is prepare in the green state. So in the green turning state, you want to prepare the part now, which may mean pre-chamfering with radii so that you have smooth entry and exit so that you're not coming in abruptly with the CBN or ceramic type cutting medium to not shock the tool initially. That will give you better part roundness, which obviously will give you better cylindricity. Holes and slots should be chamfered. You may want to hold a tighter tolerance, and again, this is and smoother surface finish is based on what the final part tolerance is. What we look at here is the tighter the part print tolerance for the final component, the tighter we try to hold it in the green state. Because what you'll find is that tool pressure plays a great deal in hard turning. So if you have just as an example, a 4 Rockwell C spread on the hardness, that is greatly going to affect what your finished size holding capability could be. Same thing as far as the amount of stock you're leaving. If you're leaving plus or minus 5 thousandths, and one part comes in on the high end and one part comes in on the low end, you're going to change the tool deflection, which ultimately is going to affect your final part size. So you may have to consider tightening up some of these tolerances in the green state in order to be more successful when you get into the hard turning, particularly for the tighter tolerance type of components. Also, smoother surface finishes. What that will do is it will give you better reliability and consistency of tool life. One thing that we've found over time is that CBN is a great cutting tool medium, but it does not like inconsistency. The more consistent you can have the part, the more consistent the tool life is going to remain. Another process strategies that we look at here, do we take a one-cut versus a two-cut strategy? Well, a one-cut strategy works really good. It's a lot quicker, shorter cycle time. Using one insert, it's only one tool position. where you're going to probably get a little bit lower surface quality. You're probably going to have to index the tool a little bit more. You're probably going to adjust for tolerance more, and there could be some shape deviation on the workpiece, meaning a little bit more out of roundness, depending upon how out of round the parts were when they came out of heat treat. Versus a two-cut strategy. And a lot of times we'll go to a two-cut strategy if we have a lot of out of roundness in the component, if we weren't maintaining a consistent amount of stock removal for the hard turn process, where basically we come in with a dedicated roughing tool. A lot of times we'll use a ceramic for that tool because it is less expensive. Machine a consistent amount of stock removal, leaving that for the finish tool, which typically would be a CBN. So we'd have a dedicated roughing tool and a finishing tool. You'll typically get longer tool life. You'll have better process stability, higher shape, and higher surface qualities. However, your cycle time is going to be affected, as well as your tooling costs to some extent. So it really comes down to, what is the final part print tolerance that you're trying to achieve. Another key strategy, when we get into turning to a square shoulder, we have to watch the lead angle on the tool and the amount of stock that we've left on the shoulder. If we leave too much stock on the shoulder, then you'll notice here that the 5-degree lead angle in this example would actually cut into the area above the CBN and cause the CBN to potentially chip out. So we want to avoid facing up shoulders, particularly when we're trying to hold precision lengths. Typically what we will do is face down the shoulder to the diameter and then move back to the beginning of the diameter and turn the diameter. That way we will have a much more stable process. Another big area today is with the advent of some of the edges that are out there, the standard radiuses versus wipers. And wipers are a great thing to use if you can get into particularly if it's a straight turn or a straight face, because essentially you can double the feed rate and maintain the same surface finish. And what's that mean? Well, basically it means you're going to be in cut for half the amount of time, which is going to double your tool life typically. However, if you need a finer surface finish, if you maintain the same surface finish, or the same feed rate, it will give you twice as good a surface finish. So just some things to keep in mind between a wiper and a standard insert and where they may apply. Interrupted cutting conditions. We get a lot of questions on this here when we get part prints in for review. Can we do an interrupted cut through a keyway or through a spline or through a gear? Yeah, you can. There's a couple of things we want to watch out for. You'll notice here on the left, the abrupt sharp corners. We want to try to minimize those at all costs, because what that does is it sets up a very, very hard impact on the tool, which could cause the tool to prematurely fail. Where if in the green state we can produce the component with some chamfers that are slightly larger than what the depth of cut is going to be, then we will have a much more finer lead in and have a less abrupt cutting condition going in. What that's going to do is it's going to increase our tool life, but it's also going to give us better part roundness and better surface finish, as well as eliminate what I call witnessing, which is the shadowing that you see a lot of times after you have passed over an interrupted cutted area. So again, take the time in the green state to prepare the part then, if you can. The other big thing that will help us when we get into interrupted cutting is to really look at the cutting tool itself. And we're going to talk a little bit about cutting tools here momentarily. Some other key process strategies for precision hard turning. Make the cutting process as stable as possible. We want to keep the shortest length to diameter ratio as we can on tools and workpieces. Keep the component clamped as close as you can to the spindle. If you have a colleted spindle, you're going to be much better off versus in a 3-jaw chuck. Tool centerline height becomes very, very critical in hard turning, particularly when it comes to tool life. We've seen a lot of studies here that we've done in our manufacturing area where we've had difficulty maintaining tool life, and we've gone down and actually put a microscope on the spindle of the machine in production and found that the tool was, maybe 6 or 8 thousandths high. when we dial that tool back down to tool centerline height or the actual spindle centerline, we've actually taken the tool life from 50 pieces to 300 or 350 pieces in some instances. So just some basics, but again, very, very critical when it comes to hard turning. Try to use a wiper as a first choice. Choose the optimum nose radius or the largest nose radius you can so that you get the maximum edge strength. Use the highest feed rates that you can. That will give you longer tool life due to shorter in-cut or contact time. Lower speeds typically will result in better system stability, and then choose a one-cut or a two-cut strategy depending upon the quality, demands, and the strength of the setup. When we start looking at the cutting tool materials, this is a pretty basic chart. You'll find this in most of the most of the tooling vendors' catalogs or something similar to this. And basically what it shows is on the right side of the chart, we have high-speed steel. And you'll notice that that's very tough material, but it has very little wear resistance. Going all the way to the upper left, where we have a diamond, which is very wear resistant, but it doesn't have a lot of toughness. And then in between there, we have things like your uncoated carbides, coated carbides, cermets, ceramics, and either CBN or PCBN, which is your cubic boron nitride products. You can actually hard turn with coated carbide, although you will be going at a very slow surface footage, probably not taking a very heavy depth of cut, and you're not going to get very good tool life. But you'll find that it is very tough, but it doesn't have a lot of wear resistance. That's where CBN or PCBN and ceramics come in. They have a great deal of wear resistance, but they don't have a lot of toughness. And because they don't have a lot of toughness, there's things that's called the edge preparations that most tool suppliers will have as standard on some of these inserts. So it's really important that we understand where these things apply. You'll notice that diamond is listed there as it is the hardest material known to mankind. However, because it is consistent of carbon, you will have a chemical interaction with the steel and you'll have catastrophic failure very quickly with a diamond. If we look at typically CBN content, and really that's where I'm going to concentrate most of today's discussion on, is CBN or PCBN, which is cubic boron nitride or polycrystalline cubic boron nitride, depending on the terminology. But basically it's a centered mass of CBN grains with binders made from ceramics, metals, and metallic borides and nitrides and some other things. And basically you'll have a couple of different types of CBN percentage contents. And where do they really apply? Well, you'll notice that on the lower end you'll have anywhere from about a 40% CBN content all the way up to around a 90% CBN content. And you'll see this with most tooling suppliers will have various different grades. And that's really what they're referring to on their grades is the amount of CBN content. A low content CBN insert is typically best used for continuous cuts and finishing. Because it doesn't have a lot of CBN content in it, it's not very, it doesn't have a lot of impact resistance. And typically the grain size is also smaller, which gives it the ability to finish, do very, very fine finishing cuts, continuous cuts. It works great. And then you'll get all the way up into something with like maybe a 90% CBN content. A 90% CBN content, on the other hand, has a lot of CBN content. Typically, the CBN particles are larger, so the particle size is larger, and basically it's building a stronger tool. And that's actually made more for interrupted cuts, very heavily interrupted cuts. And you'll see there could be various different types of grades based on CBN content, depending upon who your specific tooling vendors are. Here, if we take a look, this is just an example of applying the right type of CBN content in the right application. If you notice on the left side of this slide, we have a continuous turning operation where with a 50% CBN content, you'll notice we get about 100%, and that's basically how this chart is laid out, is that 100% would be perfect. So with a 50% CBN content tool, I'd get 100% tool life. If I misapplied the CBN content and went to a higher grade, such as an 85% CBN content is shown here, you'll notice that my tool life is going to drop significantly because the CBN content is too great. But on the other hand, if you look at an interrupted turning operation, the 85% CBN content will give me the best tool life, where 50% content, again, is going to dramatically be reduced in tool life. Again, it's just it's a misapplication for the CBN content. So you really want to pay attention and work with your tooling suppliers that are out there so that you're applying the correct CBN content in the correct application. Some of the benefits of CBN obviously are increased productivity. You're running at higher cutting speeds, and we're talking versus carbides and typically ceramics at this point. Excuse me. Higher feed rates, longer tool life. You have less machine downtime because you're not changing tool as much. And it's relatively inexpensive when you look at it from a per piece cost standpoint. If we go into the next area, we're going to look at now guidelines for some edge geometry. And this is really where most people have the least amount of understanding. And this is probably one of the more key areas to understand when we're selecting a CBN tool along with the CBN content. You notice here that basically what an edge geometry is if you look at a CBN or a ceramic insert, you'll notice very typically a chamfered edge all the way around it. That chamfered edge oftentimes is called a T-land, a K-land, an S-land. There's numerous different designations for it depending upon who your tooling supplier is. But basically it's a chamfer that runs around the top edge of the insert, which is what you're actually cutting with. And based on how that edge preparation is set up on that tool, could give you good success or not so good success based on your application. So if we take a look here at a sharp positive or neutral edge type tool, which means it has a very, very slight edge prep, very small chamfer, or possibly just a honed edge or a radiused edge. Some of the advantages of that are lower cutting forces, lower tool workpiece deflection, and lower temperatures. So you're not going to induce chatter on a part. So if you're looking at a long shaft that's a continuous cut, you might want to go to something that has a low percentage of CBN content with a very sharp edge to it. What that does is it will cut down on your cutting forces so you're not as likely to induce chatter into the workpiece. Some of the disadvantages of a sharp positive or neutral edge like that, it's a weaker edge. You have less resistance to impact, so it doesn't handle interrupted cuts very well. On the opposite end of the spectrum, you'll notice a very heavy edge prep. So we've got a steeper angle, we've got a longer chamfer length, we've got a larger radius on the hone. What that does is it gives us higher resistance to edge chipping in interrupted cutting. It will also, from some of the negatives you'll notice here, it will develop higher cutting forces, temperatures, and it will also try to deflect the tool and the workpiece much more. So a lot of times when we're looking at components here, depending upon what features we're machining on the part, we may run 3 or 4 different types of tools with different edge preps and different CBN contents. Now, I recall doing a part here years ago that was a pump shaft that had a very heavily interrupted gear in one section of it, but it had a very long shaft or straight turn on another area of it. And we actually set that up with different edge preps with different CBN content tools to handle the specific operations. So on the longer straight shaft that was uninterrupted, we'd go with a more up sharp type tool with a lower CBN content. And in the very heavily interrupted areas, we went to a very heavy edge prep with a very high CBN content to be very successful with that. Okay, move along. There it goes. Here again is just some of the demands on the edge prep, and this is just basically showing you a percentage of tool life in an interrupted cutting and a continuous cutting environment based on the angle of the chamfer. And you'll notice in the interrupted cutting, the greater the angle of the chamfer, the more increase in tool life we'll see. Again, because that's building a stronger edge. So it gives us much more impact resistance. Where on the other hand, if you notice, in a continuous cutting environment, the steeper the angle, the less amount of tool life we're going to accomplish or have. So again, it's just to go back and reinforce, that we really have to apply the right edge preparation along with the right CBN content when we're looking at our applications. What are some of the results we can expect? Well, these are some test results that we've done, and this is a part that Hardinge has ran at a number of machine tool shows over the years. And it's really what you don't see on this part that may open up some of your eyes as to what's actually achievable. If you look on the left side here, you'll see a series of 3 parts. It's all the same part, and what we do is we check this part for specific different features. We check the ball on the end of it for sphericity. We check the next diameter in, which is actually the middle diagram, which is a 200-inch radius. We check the next diameter back, which is the red, white, and blue diameter shown in the diagram. And on that diameter, we actually have 3 1/10,000th on diameter steps that we've actually moved. And then the last diameter to the far left, we actually check for cylindricity. And what are some of the achievable results that we've been able to achieve? And you can see here on the upper left, we have the sphere, and then we throw a total tolerance on that of plus or minus 60 millionths. And you'll notice the line, we actually have a theoretical ball in the center with the upper and lower tolerance bands, along with the red or magenta line indicating where we actually profiled that at. On the upper right, you'll notice the 200-inch radius. Again, with the theoretically perfect radius in red, and then the upper and lower tolerance bands. The thing you want to notice on those 2 charts in particular is that you're not seeing a lot of stick slip in the axis motion, meaning that when we get to the 12 o'clock position on that part, you'll notice that there's a very, very smooth axis reversal. It's not a real choppy move going up one side and down the other. It's a very, very smooth transition all the way around the machine. That's due to the feedback resolution, the control resolution, machine rigidity, spindle accuracy, and etc. that gives us the ability to accomplish that. That's what gives us good form. If you look down on the lower left, you'll see the chart with a red 3 steps, and then the black line indicates where we actually interpolated those steps at. Now, don't let that chart fool you. Those increments going up and down are in 10 millionths increments. So you can see that step was done within about a 5 millionth step on the first one and within 10 millionths on the second step. So very, very accurate, very controlled. You can definitely see it. And then on the far right, bottom corner, you'll see the cylindricity of that particular diameter, which it's kind of hard to read on here, but that cylindricity was actually down to around 20 millionths of an inch. So that's some of the things that are achievable when you get the right setup, the right rigidity, the right tooling, and the right process developed. These are just some examples of some real-world examples that we've done over the years. You can see some shafts and gears and pump gears and form rolls, spindle shafts, bearings, things of that nature. These are all very, very good applications for hard turning. Punches, as an example. These are just a couple of examples of some punches. These particular ones on the top, that particular customer now actually does not do any rough turning and then heat treating and grinding, which was his traditional method of manufacture. He actually stocks centerless ground through hardened blanks that we throw on a machine, and we sit and spin the end on it, rough it, finish it, and then he's able to ship it. And what that's done is taken his lead times down from 7 to 10 days down to a day. So good applications for hard turning, particularly precision hard turning. big area that we're into here is the bearing industry. This is probably one of the biggest areas that most of our requests are now coming in from, is for the bearing industries. These are just some different examples of some different types of bearings that we've done over the years. Mold and die industry, again, very, very big area for hard turning. We get into the mold and die industry. This is, again, a growing area. A lot of these customers are looking at eliminating grinding because of the expense of it. This is a real-world example here of this is actually an automotive component that we did for a large automotive supplier, where basically they were having a little bit of an issue in production on that straight hub diameter there, and you can see the original part profile was actually coming in on the cylindricity of a little over 232 millionths of an inch, which, if you're not familiar with that term, that's a little over 2/10. And you can see they're looking for a cylindricity of 2/10 or better. So they're right on the border. And what we were able to do on the particular machine was we went in and we actually put some straightness error compensation into it, which is an electronic feature that Hardinge has developed along with FANUC to be able to allow the machine to move without the operator knowing it. And what we can actually do is map a section of the machine to make it more accurate than what it is due to the process. And what we found here is that due to the process of this part, as we were machining closer to the edges of that hub, the tool was actually pushing away. And that's what was giving us that type of a shape. So through the straightness error compensation, we're able to tweak the machine and tell it to move in different directions to actually straighten it out and get the cylindricity down to 88 millionths of an inch, which helped them in their overall production. This is another real-world example. This is HSK spindle tooling for a grinding quill manufacturer, where this component, when it's done being machined, actually gets plated. So they need very good surface finish, very good geometric form, and because these grinding quills will run in excess of 60,000 RPM, they need very good TIR. So Hardinge in our specialty work holding group actually designed and developed a special HSK spindle tooling mount so we could grip on the HSK mount and machine the shape of whatever that special form was for that particular grinding wheel. And you can see some of the SPC charts there on the right. It's kind of hard to read there, but that is a 1.34 CPK on a 5 micron tolerance that you're looking at on that particular component. So again, the ability to hold very, very tight tolerance is very achievable once you have the process and understand the cutting tools and the edge preparations and have the correct machine. This is a test runoff part that we've done for a gauge manufacturer, very large gauge manufacturer actually, where this is a ring gauge, where now all the class, I believe 2X and ring gauges are now hardboard, as well as, and because we're able to get the cylindricity down under a micron, and in this case they're now down under, I believe, a half a micron. It goes straight from the hard turning machine to a lap, and they're done with the parts. So we actually eliminated a semi-finish and finish grinding operation with one hard turning operation. A rather unique situation here is that gripping on the OD of these, we find that we distort the inside, so we actually grip these on a mag chuck, which you'll see here in the next, coming up in a couple of photos. This again, another hard turning application we did. This is for a ball stud for the automotive industry. And here you can see we're coming in and doing a finish turn on the ball stud area. And we actually have a probe on this machine that comes down and probes the part for the position, and then it comes in and probes the part after we're machining it to automatically compensate the machine for any tool wear. If we look at some of the SPC data on this, you'll see here we have a CPK of around a 2.62 with a 3.24 CP, meaning we're just kind of not targeted correctly. But again, very, very extremely tight tolerance. You'll notice that is approximately an 0.8 total tolerance, again, being held to a extremely tight CPK. What are some of the new hard turning applications we have in progress? Magnetic chucks are something that we're looking at. We've actually installed one here on one of our SP Lab machines where we have an electromagnetic chuck where we're now actually machining parts on a sub-spindle and transferring automatically to a magnetic chuck on the main spindle so that we don't have to indicate the part in. Kind of a unique process. As well as hard cutoff from bar stock is another area that we're doing a lot of investigating into right now for a lot of potential customers, and they want to run 3-foot sections of pre-hardened bar at 50 to 60 Rockwell C range, and then machine the part complete and then part it off from bar. Presents its own challenges in and of itself, where we need high pressure coolant and some other things, but that's another process area that we're looking at, as well as grinding wheels and cup grinding wheels and things of that nature on a lathe. So a lot of exciting things coming down the pipe. So to basically wrap up some of the challenges of precision hard turning, really what does it need to be successful, or how do you get successful? You really got to have the right machine tool or a very rigid machine tool. The tooling is very, very key. From CBN content to edge prep, process and process development becomes very key in understanding the process, as well as gauging, being able to gauge it. And with that ends my section of the presentation. So I'd like to turn it back over to you, Jim.
Well, thank you, Tom. This is Jim Sawyer back with you again. We've received a good number of questions, and it would be nice to get to all of them before our time is up. Let me address one that I'm probably a little more qualified, probably the only question I'm a little more qualified to answer than Tom is, and that is whether this presentation will be available later as a recording. Yes, it will. At or before 7 p.m. Eastern Standard Time today, it will be available, and you can access it using the same sign-in information that you used to join us for this live presentation. That way you can go back and look at it again, or if you have some colleagues who are interested but could not make it for whatever reason, probably some meeting somewhere, or maybe they're selling something, which would be good. They can sign in, use the information, and learn from Tom's experience on this. Tom, we have a lot of questions here. They've just sort of been avalanching down on us, but let me go to the first one that came in because it's sort of interesting. Is it completely possible to remove all witnessing marks during interrupted cuts?
I'm going to say with a real rigid setup, you could potentially get rid of 80 to 85% of the witness marks that you're seeing. Typically, when we see a lot of witnessing marks here, it comes down to the work holding or the cutting tool extension. Meaning that the tool is not rigid enough or the work holding is not rigid enough, which typically on Hardinge machines, because we do run a colleted spindle, we don't see a lot of witnessing when we get past an interruption or in an interrupted area. But typically that's where I would start looking at. Would be a couple of key areas would be the work holding rigidity. If you're in a 3-jaw chuck with standard 3 jaws, maybe try pi jaws, or maybe go to what we call a step chuck, an enclosure type setup, which basically what that does is it shortens everything up and gets you closer to your spindle bearings. Make sure that you have the least amount of tool extension that you need, and then I would also double check your tool centerline height. In a case where we're running interrupted cuts, a lot of times we'll actually set the tool on purpose, a thou to 2 thou higher above center line than setting it directly on center line. what that does is as it comes into the interruption, it will actually spring down and cut on center and cut a little bit freer for you. So there are a couple areas there you can take a look at.
All right. The questions are just pouring in.
And we'll get to what we can, and then email them to me, and I'll email back the answers in the next day or so.
Right, and I was just going to bring that up. Also, more information on this topic may be found at the following website. It is www.superprecision.com. You should see it there at the bottom of the slide on your screen, and this slide also explains that questions will be forwarded to Hardinge if they're unanswered, and an email with a response will be sent out to you. Couple of related questions. One came in right after the other. What are your thoughts on using coolant during hard turning? I have always been told not to use it. And the other one is, do you run dry?
Yeah, that's a good question, and a lot of people bring that one up. Typically, if you're in an interrupted cut situation where you are cutting through keyways, cutting through bolt hole patterns and things of that nature, you definitely want to cut dry. The reason for that is that when you come in and out of the cut in the interruption, you're actually losing the heat in and out of the tool, and what you'll do is it will actually thermal shock the insert, which will crack it and will actually cause premature failure. So in an interrupted cut application, you never want to run coolant on it. If it's a continuous cutting application, you can run coolant on it, but if you're going to run coolant on it, you want to make sure that cutting or that fluid, the coolant, is being directed right into the cutting zone. So you want to nozzle it as best you can, right down into the shear zone, maybe hit it from both sides of the tools and pour the coolant to it. Make sure you do not have an intermittent lapse of coolant, otherwise you'll thermal shock the insert. One of the benefits of using coolant, particularly when you're in a continuous cut, is that it will keep your part more temperature stable. Meaning that if you're trying to hold an extremely tight size tolerance, if you're running coolant, typically you will maintain part size a little bit easier because as we know, as the tool wears, we're going to generate more heat. And that heat typically, as we look at it from a rule of thumb, 80% of the heat should be going out in the chip, 10% should be going back into the part, and 10% back into the chip. So as the tool wears, you're going to get more part heat generation, which could affect you on size holding capability. So in that instance, yeah, typically when we run very, very tight tolerances on continuous cuts, we will run coolant. It also helps to wash the chip away so you're not recutting the chip, but mainly for size holding capability is what we do it for. But again, the key there is if you're going to run coolant, you've got to make sure you're running coolant and give it all the pressure you can give it. And make sure you don't have an intermittent lapse of coolant, otherwise you will have detrimental effects on the cutting tool.
Okay. Tom, we're getting some very specific questions here on applications, so these might be best handled via email.
Sure.
One of the questions that, or actually a couple of questions that we've gotten, one is, can we get a PDF of the slides, and will the slides be available after the presentation? Is that something that you could make available, Tom, or should we discuss that more offline?
Send it to everybody? We're going to send it. Yeah, what we're going to do is once we receive the list of attendees, we will forward out an email to all the attendees of this program presentation in a PDF format, so everybody will have a copy of that coming to them via their email.
Okay, very good. Well, thank you. We are just about at our 3 o'clock point, and the questions are very, very specific here, so we will answer those directly to the people who posed them. One of the questions that was asked is, can we post the questions and the answers to them online with a recorded version of this webinar. We'll see what we can do that. That's a great question. It would be a great service for people who've attended this. And we'll definitely look into it.
Okay.
Unfortunately, our time is up. As noted, your questions will be answered and an email sent to you. As Tom has proved with his presentation, there often are other technologies that can get you where you want to go and can often do so quicker and more efficiently than what you're using. To help you keep abreast of the latest in technology and techniques, Manufacturing Engineering Media has a host of ways by which you can keep abreast of this technology and these techniques. For instance, the March issue of Manufacturing Engineering magazine will feature articles on aerospace and defense manufacturing, including aerospace engine and component production. The April issue will have articles on machining centers and cells, as well as motorized vehicle manufacturing. In May, we're focusing on medical manufacturing, and also in the Shop Solutions department of every issue of Manufacturing Engineering, you can learn about the challenges facing shops around North America and the solutions they've arrived at to achieve success. We thank you for joining us for this Manufacturing Engineering Media webinar, and we hope you found it informative. Thank you very much.